In Module 1, we laid the foundation, understanding measurement principles, system components, signal characteristics, and data treatment. Now in Module 2, we will apply those concepts to measure specific physical quantities. Counting and timing. Dimensional measurement. Displacement and linear velocity. Strain, force, and torque. Pressure measurement. Flow measurement. Temperature measurement. Vibration and shock. Acoustical measurements. 1. Determination of count, events per unit time, and time interval. Counting is the most basic form of measurement, recording the number of occurrences of a specific event. 1.1. Counting devices. Mechanical counters, driven by gears or cams, used in older systems. Electromechanical counters, solenoid-driven mechanisms. Electronic counters, digital systems capable of high-speed operation. 1.2. Time interval measurement. Stopwatches, manual triggering, prone to human error. Electronic timers, triggered by electronic signals, very high precision. Oscilloscopes, can display and measure time between signal pulses. 2. Measurement of dimensions. Dimensional measurement ensures that manufactured components meet required tolerances. 2.1. Common instruments. Steel rules, for quick, rough measurements. Vernier calipers, for moderate precision. Micrometers, for high precision down to microns. Coordinate measuring machines, CMM, automated, highly accurate 3D measurements. 2.2. Principles of accuracy. Accuracy depends on calibration, proper contact with the object, and environmental conditions like temperature. 3. Measurement of displacement and linear velocity. Displacement measurement can be contact-based or non-contact. 3.1. Contact devices. Dia indicators, mechanical amplification of small displacements. Linear variable differential transformers, LVDTs, transform motion into an electrical signal. 3.2. Non-contact devices. Laser displacement sensors, high precision, unaffected by mechanical wear. Ultrasonic sensors, good for longer distances. 3.3. Linear velocity. Velocity can be measured by differentiating displacement data over time. Doppler-based sensors for fluids or moving surfaces. 4. Strain measurement. Strain is the fractional change in length when a material is subjected to stress. 4.1. Strain gauges. Resistive strain gauges, most common, change resistance with strain. Optical fiber strain sensors, immune to electromagnetic interference. 4.2. Installation and calibration. Correct bonding to the surface and temperature compensation are essential for accuracy. 5. Force and torque measurement. Force is measured either directly or indirectly via strain. 5.1. Force measurement. Load cells, strain gauge-based devices. Hydraulic load cells, measure fluid pressure proportional to force. Piezoelectric sensors, generate voltage when deformed. 5.2. Torque measurement. Static torque, measured using reaction methods. Rotary torque, measured via strain gauges mounted on rotating shafts with slip rings or telemetry. 6. Pressure measurement. Pressure is one of the most widely measured quantities in industry. 6.1. Types of pressure. Absolute pressure, reference to a perfect vacuum. Gauge pressure, reference to atmospheric pressure. Differential pressure, difference between 2 points. 6.2. Measurement devices. Bourdon tubes, mechanical deflection devices. Diaphragm gauges, deflection of a diaphragm. Piezoelectric sensors, a high dynamic response. Manometers, liquid column measurement. 7. Flow measurement. Flow measurement is critical in fluid systems. 7.1. Volumetric flow. Orifice plates, venturi tubes, flow nozzles, create a pressure drop related to flow rate. Rotometers, variable area flow meters with a floating bulb. 7.2. Mass flow. Coriolis flow meters, measure mass flow directly. Thermal mass flow meters, use heat transfer principles. 8. Temperature measurement. Temperature affects almost every engineering process. 8.1 Mechanical thermometers. Liquid-in-glass thermometers, expansion-based. Bimetallic strips, mechanical bending due to differential expansion. 8.2 Electrical temperature sensors. Thermocouples, voltage generated at junctions of different metals. Resistance temperature detectors, RTDs, resistance changes with temperature. Thermistors, high sensitivity over limited ranges. 8.3 Non-contact methods. Infrared pyrometers, detect emitted thermal radiation. 9. Vibration and shock measurements. These measurements are key in condition monitoring. 9.1 Vibration measurement. Accelerometers, piezoelectric, capacitive, or MEMS-based. Velocity sensors, coil and magnet type. 9.2 Shock measurement. Specialized high-G accelerometers to record transient events. 10. Acoustical measurements. Sound can reveal much about system health and environment. 10.1 Parameters measured. Sound pressure level. Frequency content. Directionality. 10.2 Equipment. Microphones convert sound to electrical signals. Sound level meters integrate sound pressure over time. Module 2 has shown how measurement principles are applied to real engineering challenges, from counting to acoustics. When you combine Module 1's theory with Module 2's applications, you gain the ability not just to operate instruments, but to design measurement systems, interpret results, and troubleshoot issues in the field.